Good afternoon, everyone, and welcome to today's webinar on acquiring and interpreting CAN message data with eDAQ hardware. Your microphone will stay muted throughout the presentation. If you have questions, we will address them at the end of the presentation using either the Q&A or chat feature of WebEx. However, you are welcome to type in the questions at any time. Our presenter today is Will Barlow. Will is an applications engineer for HBM based in the Detroit area. He spent 13 years in the automotive industry performing a variety of vehicle testing, both in the field and in the simulation lab, before he joined HBM. Will, it's all yours.
Okay. Hello, and thank you for attending today's webinar on acquiring and interpreting CAN messages with eDAQ hardware. Again, my name is Will Barlow, application engineer for HBM. This webinar will provide a brief overview of CAN communication protocols, the benefits of acquiring CAN messages, and also explore how the eDAQ can be used to record and interpret those CAN messages. During the webinar, we will go over what is CAN and CAN's origins, what can be gained from acquiring CAN messages, and how to use the eDAQ to acquire those messages. All right, what is CAN? CAN is a serial bus protocol used to connect individual systems and sensors together as an alternative to the conventional multi-wire looms. In respect to the auto industry, it allows automotive components to communicate on a single or dual-wire network data bus up to 1 megabit per second. Though it was developed for automotive applications, more and more industries like industrial machining operations, military, agricultural, medical systems are also implementing the use of CAN. All right, here's just some brief history of CAN. It was developed by Bosch in the early 80s. It was released to SAE, which is Society of Automotive Engineers, at their World Conference in 1986. By 1987, Intel had produced the first CAN chip. It was based on a non-destructive arbitration mechanism, which would grant bus access to the message with the highest priority without any delays. There is no central master bus. The identifier in the message also has the function of specifying the priority of the message within the system. Though elevator and textile manufacturers were the first adopters of CAN, in 1992, Mercedes-Benz was the first automotive manufacturer to introduce vehicles with CAN bus in the market. For the first time, the vehicle systems and sensors were able to communicate to controllers at very high speeds on a single or dual-wire communication line as opposed to the previous multi-wire looms. An additional advantage is that CAN utilizes less wires and connectors than the multi-wire looms, thus significantly reducing vehicle weight. Here's the composition of what a streaming CAN message would contain. The identifier section contains information of the priority of the message. The DLC, which is the data length code, indicates the number of bytes of data in the message. The data field is the actual data portion of the message, whose size, again, is determined by the DLC. The EOF indicates the end of frame, which contains 7 recessive bits. Because this is a brief overview, I will not cover all the components of the message. However, if you are interested in a more in-depth information about CAN, HBM does offer a eDAQ vehicle networking seminar that discusses CAN use with the eDAQ in greater detail. I'll post a link for that at the end of the webinar. All right, this slide breaks down how many bits and bytes are in the various components of a CAN message. The arbitration and control fields will total 11 or 29 bits, which is also an indicator of whether it's a CAN 2A or 2B system, respectively. With 8 bits to a byte, the eDAQ pads the arbitration and control fields so that the 11 and 29 bit fields fit in a 2 and 4 byte message, respectively. This way, the data portion will start either at bit 16 for a 11-bit message or bit 32 for a 29-bit message. The data portion can be up to 8 bytes and is written as first as most significant byte. In most significant byte, the bytes are, in a message are arranged from largest to smallest. Conversely, in least significant byte, the bytes are arranged from smallest to largest. In most and least significant bit, the bits of the individual bytes are combined together. Although the message is initially read as most significant byte from the data field, the actual data may be in different formats. In fact, many manufacturers use this as a security device, making reverse engineering of their CAN messages a little bit more difficult. In order to find out how to decode a message, you should refer to the parameter group number, the PGN, or you can also talk to whoever's written the code for that particular control unit. The identifier portion of your message will supply you the information as to what PGN it belongs to. From there, you can interpret a message based on parameters like number of bits and bytes and its ordering and location. You can also determine if scale factors and offsets need to be applied. Let's take this streaming CAN message. Note that this is not a representative of a real CAN message. It's just something that we kind of put together. It's intended only for illustrative purposes. That being said, we'll use this message to determine the engine speed using J1939. If you look at the blue field at the beginning of the message, it contains the arbitration and control fields and has 4 bytes. With 8 bits to a byte, the field contains a 29-bit message. If you examine the message closer, bytes F0 and 04 indicate that the message comes from PGN 61444. Now that we know the PGN, we can look up engine speed in order to retrieve the values needed to decipher it from the CAN message. From the PGN, we get that the bit position is equal to 56 and the bit length is equal to 16. Again, for illustrative purposes, we'll say it was written in least significant bytes and has a scalar factor of 1.25. First, we will use the bit position and length to find its location in the message. From the bit position and length, we deduce that the engine speed bytes are 38 and 03. The data is supposed to be in least significant bytes, so the order changes from 03 and bytes 38. Now we can convert these hex values to decimal, then apply a scalar factor of 1.25. This will give us a engine speed of 1,030 RPMs. Now that we know what CAN is, let's examine the advantages of acquiring these messages. For this part of the webinar, let's examine the advantages of collecting CAN messages as it pertains to RLDA, which is road load data acquisition. During an RLDA, data is acquired from any number of vehicle components and subsystems. The data is then used for numerous applications such as analysis models, component or full vehicle testing, and performance and durability studies. During an RLDA, one could be asked to acquire specific data for vehicles for any number of applications. Data like engine and vehicle speed, coolant temps, oil pressures, and brake applications are commonly requested. In order to collect the data, the various sensors, like the one shown on this slide, will have to be installed, and their analog signals would then be outputted to a data acquisition system such as an eDAQ. However, most, if not all, vehicles contain sensors that measure the data of interest. These sensors are tied into the vehicle's CAN bus, delivering information to various control units. With the eDAQ, you have the ability to acquire the data from the vehicle's CAN. This is an excerpt of a J1939 database which illustrates just a handful of channels available from the CAN. The highlighted speed, temperature, and pressure channels are the data channels that would have been previously acquired through analog means. Now we can measure those channels without having to add sensors and then taking the time to install those sensors. So we're saving resources that way. Besides acquiring data from the vehicle CAN, you also have the ability to connect CAN sensors to the eDAQ. By using CAN sensors connected to the eDAQ, you can eliminate the use of multiple analog channels. This is especially evident with wheel force transducers. Typically, wheel force transducers take up to 32 analog channels to measure the force and moments of 4 wheels. With CAN wheel force transducers, you can eliminate the need to connect them through analog, thus saving acquisition resources. Now that I've discussed the advantages of acquiring CAN messages, let's talk about how to acquire CAN messages with an eDAQ. There are 3 ways via hardware to acquire CAN messages with an eDAQ. First, you could use a high-level board with a vehicle bus that's integrated into the base layer. However, this model has been discontinued. The second way would be to connect a Somat vehicle bus module to the DIO layer. These modules allow certain banks in the DIO to accept vehicle network parameters. Though this webinar will focus primarily on CAN with J1939, the eDAQ does support other parameters which are listed on this slide, such as single wire CAN, J1708, J1850, and ISO 9141. Lastly, if you have an eDAQ Plus or eDAQ Lite, you can attach an ECON or ELCOM layer to it. The ECOM layer is a 5-port communications layer equipped with 3 CAN ports, 1 vehicle bus port, and 1 GPS port. The CAN port, which is protocol 2B, has selectable baud rates ranging from 41.6 kilobits to 1 megabit per second. The ECOM layer also has the ability to power CAN-based transducers with 3 to 24 volts, and you can log up to 256 messages per port. The ECOM layer is also equipped with a vehicle bus port that has all the same advantages of the CAN port, but it works with the wide array of vehicle bus modules from the previous slide. The ELCOM layer, which I have pictured here, works the same as the ECOM layer, but it's used for eDAQ Lite. In order to retrieve CAN messages, you will need to connect your eDAQ CAN port to the vehicle's diagnostic port. On passenger vehicles, connect the OBD2 CAN high, CAN low, and ground to the respective ones on the eDAQ CAN port. Heavy-duty vehicles have different types of connector designs, but essentially you still connect it to the CAN high, CAN low, and ground. One thing to consider is even though the eDAQ is passively monitoring messages on the CAN network, it does have electrical implications if the connection does not include termination. Without termination, the connecting cables could become reflective and could prevent communication. This is corrected by ensuring that the line has a terminator resistor across the high and low lines of the source. Typically, a CAN-based system is 120 ohms. You would use a 120 ohm resistor for a CAN-based system. Your vehicle OBD2 connector may already be equipped with a terminating resistor. I suggest taking an ohm meter and checking the resistance between the CAN high and CAN low to determine if you need to add one. The eDAQ itself already has internal termination, which you can apply yourself, and we'll see in later slides. Once the eDAQ is connected to your vehicle, you can now begin to acquire CAN messages. In order to collect CAN messages, there needs to be an associated database. Without a database, the eDAQ cannot correctly interpret the message just streaming from the network. Databases are stored in the following directories of the eDAQ. To get to them via the web browser, you will put in your eDAQ's IP address into a browser page. When that pulls up under System Maintenance, you would select the Explore eDAQ files. From there, you would go into the Users folder, then the Setup folder, Databases, and Vehicle Bus. From Vehicle Bus, you can determine what folder you would like to add your databases to. In our instance, we're going to go into the CAN folder. Okay, once you are in the CAN directory, you can add, view, edit, or delete databases. Also in this directory, you have the ability to edit the database that's already uploaded into the eDAQ. So if you already have a database that's in your eDAQ and you want to make some modifications to it, you can do it right there in the eDAQ. If you select Spreadsheet next to the appropriate database that you would like to edit, your database will appear in spreadsheet form. So here's the columns for the J1939 database. And this next slide is just a continuation of those columns. So I couldn't fit them all on one sheet where you could still read the headers next to it. Though it's possible to edit the database in the eDAQ, for redundancy and ease of editing, I always recommend that you download the database. Once the database is downloaded from the eDAQ, it appears as a text file. You can then import that text file into an Excel spreadsheet and then edit the database from there. This right here is an excerpt from a standard J1939 database that has been imported into an Excel spreadsheet. The data under the column headings may be edited. Here are the specific headings for the database and the descriptions of what they're used for. The ID field is a specific identifier for the channel, and it follows the same rules as TCE, limited to 12 characters, so on and so forth. The interface describes the protocol that's used. Somat uses a masking to guarantee that the incoming messages truly are correct for the data that that's being sought. This mask is applied to incoming messages, and the resulting value is then compared against the value to confirm the messages are indeed correct. The description provides greater detail for a specific channel. It's similar to the description in TCE where since you're only limited to the 12 characters in the ID, you can then write a more in-depth description in descriptions. Bit pos, or bit position, is a field that defines where on the message the actual required data resides. The accuracy of the bit position is very important, as more than one data value could reside on the same message block. Data length defines the resolution value for the data portion of the message. Effectively, this is the stop point from the start point defined by the bit position heading. For example, if your bit position is 32 and your bit length is 8, the data portion of the message will start at bit 32 and it will go through bit 40, bit position 40. Measuring and units just describe the engineering units that will be used in your database. Offset and scales describe any changes that need to be made to the data to produce an accurate representation of the measurements. Min and max are the lowest and highest values expected, respectively. And the data format is used in conjunction with the bit position and bit length, and define whether the data is read in least or most significant formats. Typically, if you look at the list here, if you start at the bit position to the data format, the values for those can be found in your PGN or whoever's written the code for your controller. Some messages require that the controller be requested to broadcast that data value. So there is a way, we do have fields to where you can make a request and request waits that will accommodate that. So you're able to ask the controller to send data to you. Once the data is uploaded into the eDAQ, if you've chosen, or if you've chosen to use our standard databases, I guess I should have mentioned at some point the eDAQ does have some of the standard databases already in the eDAQ. You can begin to receive CAN messages with your eDAQ. All right, before you open TCE and set up a test, I always recommend that you attempt to get the CAN messages via the web browser. That way you can assure that the eDAQ is communicating with your CAN network. To do that, once you've connected to your eDAQ via web browser, you would select the hardware tab, and then under the card type column, just select the CAN vehicle bus link. I guess just a side note before I continue is if you look up above at the vehicle bus, if you select the edit parameter databases, you can get to the vehicle databases versus going through the whole gamut of directories that I showed you earlier. To start logging messages, you want to select the CAN port that your network is connected to, and then you want to configure those settings. Typically, the only setting you'll need to edit would be the baud rate. Make sure that the eDAQ's CAN baud rate is set the same as your CAN source. Conflicting baud rates will result in non-communication. Once the baud rate is set, select the log message button. If you select the button and nothing happens, something is preventing communication. Typically, this is a result of either incorrect baud rate or it could be a problem with your termination. However, if you start receiving messages, it'll appear in your browser window. So when you start receiving messages, you should immediately hit the stop button on your browser. If you don't, the messages will continue to stream to your browser until it fills up your cache. Once you've received your messages, if you want, you can go back to where you configure your CAN and select your database from your pull down and log messages again. Since that time you would have a database associated with it, your messages should appear as engineering units. And if we take a look at this message that I have on the screen right now, if you see back from earlier examples when we were trying to determine engine speed, and we know the bit call out, the byte call out was F004 for engine speed. We can now determine from here where engine speed is, and I've circled a few of the engine speeds. And if you notice, as you go down the row to the right, to the corresponding row, that it starts off at 000, which means more likely the engine is not spinning, and then it changes to bytes 4601, which indicates something is happening, that is collecting some type of data, and then 4602, which means there is the engine is turning, or you are collecting some RPM data. And then I guess I should mention also to the right, to the left of the message at the beginning, after the RX, that's the time that the message is being broadcast. It's not real time; it's just a time associated from when the message is being broadcast. To set up CAN messages in TCE, you can do this. You can achieve this by going into the hardware setup page and then double-clicking on your CAN port. I guess, of course, you need to query first so it can recognize all your hardware. And then I guess one thing I would like to mention real quick is that if you are connecting via from the DIO or using any type of vehicle bus module to measure CAN, that if you try to add one after you've already queried, that you're going to have to shut your eDAQ down and repower again, so that the eDAQ can recognize you have loaded new hardware, because it's the equivalent of adding a layer to your eDAQ. So again, if you do add a vehicle bus module, so while the eDAQ is already powered, you're going to need to power again, power down and come back up again, so the eDAQ can't recognize it. All right. So once you've double-clicked on on your vehicle bus, you could then select your database that you want to associate with that CAN hardware. And from there, you can select the hardware interface specifics to set power for CAN transducers in case you're using some type of CAN transducer that requires power. You can also, this is where you would also set your baud rate for that. And then this is where you also enable internal termination. Once your CAN is set up, you can add CAN channels to your test by selecting the Add button in the transducer and message channel setup page. Select the vehicle bus and then via whatever hardware you connect it to. In our case, we're connected to the COM layer, so we're going to select vehicle bus COM. Then select the message you would like to capture. When the message is selected, it will be added to the transducer setup page. Edit that sensor, for instance, sample rate or the output sample rate, like you would any other channel you're acquiring for TCE. Once that channel has been added to a data mode, you can start collecting. You can then start collecting that data just like any other analog channel you would with TCE. So that concludes my portion of today's webinar, and I'd like to thank you for attending. If you wanted more information about the vehicle networking, HBM does offer the following seminar, eDAQ Vehicle Networking Training Seminar, and below that is a link to it, or you can look on our HBM web page and go to the training section to find the seminar. Thank you.
Thanks, Will. And we have one question came in, Will. Here, can the eDAQ transmit any CAN messages?
The eDAQ cannot transmit any CAN messages. The eDAQ only acts as like a passive. It only passively monitors the network. What the eDAQ can do is query for specific messages, but it cannot be used to send out CAN messages.
Here's another question. Do you have any suggestions for different types of sensors, like manufacturers that make sensors that would be CAN compatible?
I guess I don't have any, I guess off the top of my head. If you could tell me, if you want to maybe let me know what type of sensor you're looking for, and I could maybe try to help you find something that's going to be compatible with our eDAQ.
All right. If a message is not broadcasted, is it possible to program it so that you can view it?
Well, you can do the active query, because typically with active querying, those messages aren't broadcast. So you would have to know, I guess, the address. You would have to request for that address.
Okay. So if you knew the specific address of the message, then you could possibly get it. All right. And as far as the database goes, how do you choose a priority for the message?
Typically, that's done by the PGN or whoever's writing the controller. I mean, there is I guess bit ordering for the priorities of a message. I believe it's 1 through 7 or 1 through 3, but there is bit ordering for the priority. So I guess there is a possible way to set it, but typically it's done if you're using a database, it's already done in the database.
All right. Is it possible to monitor messages to perform custom triggers?
Yes, there is. I mean, once you start it, essentially once you start monitoring, once you start collecting data, it's no different than streaming any type of analog data to the system. So long as there's, as long as you're triggering off some type of CAN event, it should be fine.
All right. Another question, how do you set up a 29-bit or 11-bit identifier?
Well, typically, like I said, it's normally set up in the, it's normally set up from whoever's written up that database. Set up yourself, I'll have to get back with you on that to actually set it up yourself, but normally it's set up from whoever's writing the database for whatever you're trying to collect.
All right. Well, everyone, thank you very much for attending today. If we didn't get to your message or your question, we'll get back to you directly in the next few days. Thank you very much for joining us, and enjoy the rest of your afternoon.